Hello, Wildcats. It's a good day to do some physics. It's Friday, and check it out. I got my special green vegetable Hobbit drink that gives me extra Shire power. I got my G2s lined up here, ready to go. And last but not least, check this out. Oh yeah. I got myself some FPC, French press coffee. Oh man, what else do you need? Some physics problems. You need that. Okay, so here's what we're going to do. I'm going to do some of these with you, and you can take notes. Others of them I'm just going to start for you. And this is the last video for independent study number 4. So, let's get going. Determine symbolically, all right, no numbers here, the magnitude of the velocity on the electron of a hydrogen atom exerted by a single proton that is its nucleus, assuming it is a circular path. Okay, now particle physicists don't really like this model because it's actually much more complicated than just an orbit that looks like that. But this is called the Bohr Model, and it just kind of helps us to look at atoms a little bit. We're going to assume that the path is circular, and we're looking at the force here. Okay, so what we can say is that Fc is equal to the electric force. Okay, so we know that Fc can be caused by tension, force of friction, even normal force, and force of gravity. We've talked about all those, but centripetal force could also be caused by electric force. Okay. Let's draw an FBD on the electron. Fe, electrostatic force. That's it. We never put Fc on an FBD. And that will give us, that's the whole free body diagram right there. Okay, so what we can do is say m, we're talking about the mass of the electron, v squared over radius, is equal to electrostatic force. Okay, so that's going to be Coulombs Law constant, charge of an electron, charge of the proton, divided by their radius squared. Okay, now why the mass of the electron in the centripetal force equation? When we're talking Fc, it's always the mass of the thing that is actually orbiting, okay, not the mass of the central object. Alright, so we got to keep that straight. Okay, so some things cancel. Radius is gone, squared is gone, and let's see, I guess that's all I can cancel for now. Okay, so now we just need to solve for velocity. That's what we're asked to get. We can say velocity is equal to square root of this big ugly thing here, and that's going to be k times QE, charge of the proton, over 1 radius times the mass of an electron. Okay, now check this out. This is how AP problems go a lot. Solve for something in terms of something else in fundamental constants. Okay, that means things that don't change, things that are always the same. So mass of an electron, charge of a proton, charge of an electron, and K, those are all constants. Alright, now we're not actually going to plug this in, but keep in mind your constants page. Okay, has all of these values. You don't have to memorize them. Okay, let's look at this one. This is huge. Okay, this will be tested in multiple places in this class. What is larger in amplitude? The the force that Q1 exerts on Q2 or the force that Q2 exerts on Q1. So what we've got are these charges sitting out in space, and they've got some distance radius. This one is 50 microcoulombs. The micro printed out in the wrong spot. This one is 1 microcoulomb. Okay, now you will need these metric units a lot. The unit coulomb is actually really big, so a lot of times we're talking microcoulombs. You might see maybe millicoulombs. Okay, micro is going to be times 10 to the minus 6, a millionth of a coulomb. Okay, so this charge is 50 times this charge over here. Okay, so which one is going to get a greater magnitude of force? Since this one's so big, isn't this one going to get a greater force on it? Wrong. No. That would be the trick in this question. The answer is same force. Why? Why same force? Okay, you need to write an explanation why the forces on this one are the same as the force on this one. Okay, these are both positive charge. This one's going to get a repulsive force, say F1. This one is also going to get a repulsive force, say F2. They're going to be the same amount of newtons. Why? Tell me why down here. Okay, you're going to think back to stuff that you learned a long time ago. There's a key phrase you need to get example 2 correct. Alright, so finish that up. Okay, let's go on to the back here. Alright, this is a mathematical problem here that we need to deal with. 3 charged particles are arranged in a line. Calculate the net electrostatic force on particle 3 due to the other 2 charges. Okay, so we need to draw an FBD down here. So this is Q3. And what we like to do on these types of problems where we've got 3 or 4 or 5 particles is really just focus on one particle at a time. Okay, so we want the force on charge 3. We don't really care about the forces on these other 2. So what I'm going to do is I'm going to start by covering this one up. I'm going to pretend that it's not even there. Alright, and it just kind of helps us visualize a little bit. Electrostatic force can be attractive or repulsive. So between these 2, this one is attracted to that one. Okay, opposites attract. So what we are going to do is draw a force vector in this direction, and I'm going to label it force on charge 3 due to charge 2, 3-2. Okay. Alright, now here's where it gets kind of confusing for people. If I take my finger off that, alright, these 2, yes, they have a force on each other, but the force between these 2 does not affect what's happening between this one and this one. Okay, people like to say, oh, there's this one in between, so that's going to mess things up somehow. It actually doesn't. What I'm going to do is now cover this one up and pretend it's not even there. And this is a repulsive force, so this one does not like the fact that that one's there. Alright, so there's going to be a force in this direction. I'm going to draw them the same length. I don't know which one's bigger until I do the math. And I'm going to say this is the force on charge 3 due to charge 1. Okay? Alright, so that's my FBD. We want the net electrostatic force. So I'm going to have to calculate that, and then get the net force. Okay? So you're going to use Coulombs Law 2 times. I'm going to let you finish that one. And I'll check the answer. Let's see. One more thing that I'm going to say. When we use this, you might have noticed that on your equations page, they absolute value this whole thing. And that's because the sign does not matter. The sign doesn't actually tell us the direction, really. It just tells us if it is an attractive or a repulsive force. So when we use this, we always drop the signs. So these negatives, don't even plug them in. Okay, what you want to do is plug everything in without negatives, and then label your force over here on your FBD. That will tell you the direction. Okay? All right, finish that one up. Okay, let's look at this one. Read it, understand it before you actually do this. Okay, I'm going to show you an example of how to do this one and this one, and then I'm going to let you complete the rest of them. We're going to rank the electrostatic force on a particle put at point P. Okay, here's the deal. It doesn't tell us what kind of charge we're going to put there, but it actually doesn't matter. We could pretend we're putting a positive charge at point P all over, or a negative, and it wouldn't change the force. Okay? It would change the direction due to these, but it's not going to change the value. So what I'm going to do is put a negative Q at each of these points. Okay, I'm going to pretend I'm putting a negative charge at each of those points. Then I'm going to analyze the directions and the magnitudes. Okay, so let's look at Coulombs Law. KQ over R squared. I'm going to do the same thing I did up here. What's up? Yeah, I'm doing a video for like an independent study. Yeah, I do. There you go.
Do you have kids coming in today?
No. No, I just have to film this, so they're doing it online. It's like a, yeah. Cameo from Mr. Husky, everyone. All right, have a good day.
Yeah, buddy. I'll bring you right back.
Okay, cool. All right, so we're going to place that charge there, and we're going to do the same thing we did up here. Okay, so I've got a negative Q here now. So the force due to this one on this one is going to be a repulsive force, and the Q's are the same on this whole page. Everything is the same charge. So I don't even care about the top of this. What I care about is that the force is proportional to 1 over R squared. Alright, so get in there. Cool. You're welcome. Okay, so I'm going to get a force. I'm going to call this a force of value 1, and I'm going to draw it one length here. Okay, and that's what I just decided, and you'll kind of see what I'm talking about when I do example B. You'll sort of catch on. So be patient with this first example. Okay, now what I'm going to do, I'm going to cover that one up, pretend that it doesn't exist, and the force due to that one on that one is going to be like this. And it's going to be the same magnitude, so I drew it the same length. So I'm going to say the force net is equal to 0. Alright? Okay, now let's look at this one. I'm going to put a negative Q here. I'm just going to put a negative sign. I'm going to cover this up. This is a distance 1 away. So, again, I'm going to get a repulsive force that looks like that due to that one. Okay. Now it gets interesting. Let's cover this one up. We know this is going to be an attractive force between these two. But this is twice the distance that I had here, here, and here. Okay, let's look at our equation. If I have 1 over 2r squared, you know that that becomes a fourth times 1 over r squared. So my force is a quarter of what all of these forces would be. So I'm going to draw this vector a quarter is big. So my net force is a force of 1 minus a force of 0.25. So I'm going to say F net is equal to 0.75. Alright, now these are not actual newtons. These are just numbers that I'm using to compare all of these and rank them. Okay, you should be able to do the rest. Essay question. Okay, you can watch some of the previous videos. I think it's in video, let's see, video 2 will help you out with the essay question. Okay, you have to compare the force of gravity and electric force and contrast them, and then you have to write a short essay. Okay, so the Venn diagram helps you plan your essay. Alright, this one. I got imbalanced charge on these things. The switch gets closed, okay? And when this switch gets closed, these are going to equalize. So I've got a total charge of 90. They're going to equalize to 45 nanocoulombs. And they're going to be the same, okay? Alright, now part E and F, smaller spheres, but still going to equalize. Okay, here we have an imbalance. Which one can hold more? Okay, I've got a large sphere and a small sphere. Think about the Van de Graaff generator. Okay, and what we learned with that, which one of these is going to hold more charge? Okay, it's not a trick question, by the way. Okay, see if you can rank these. Rank the electric charge after they are closed. Okay, this ranking task, I'm going to change it. I don't want you to rank it, okay? It's a huge pain. This is what I want you to do. On the bottom left charge, all I want you to do is draw an FBD for each bottom left charge. That's all I want you to do. And I want you to draw it roughly proportional. Okay, so I'll do the first one for you. These distances are all the same. Okay, in the first one, there were different distances, same charge. Here, same distances, and we're looking at charge magnitude. Okay, these are positive here. So the force, I'm going to cover this one up. The force on this due to this is repulsive, and I'm going to draw a length 4 because I've got 2 times 2. Okay, I'm going to cover this one up. The force on this one due to this one is a magnitude 2 vector because I've got a 2 times a 1. That's my FBD. That's all I want you to do for these. Now if I gave you values, you could do a vector scorecard, and you could add the x and y components, and it would be a huge pain. And you could get F net. Okay, the net force vector, by the way, is going to be this vector moved parallel to itself. I'm drawing these tip to tail. The net would be right here, splitting these, and it would be that length. Okay, you don't have to do this on these. Okay, that's actually not a FBD because that's F net, and we don't put F nets on an FBD. Okay, alright, finish these. One of the keys is to make sure this is all in a line, and this is all in a line here. Okay, so here your forces need to be along these lines on all of these. They need to be along this line and along this line here. Okay, have fun, draw some FBDs. This one is the true test to see if you know what you're doing with Coulombs Law. If you can do this one and understand it completely, then you got it. there's not much else I could ask you besides this question. So this is the big test right here. Okay. Sit down with a buddy, work on these, and finish all the ones that we didn't do together. Thanks for watching.